Okay, in this video we are going to work out a few more Laplace transforms, specifically for e to the at and then te to the at. So let's get started. So we're looking for the Laplace transform of e to the at, and we know by definition that's going to be the integral from 0 to infinity of our function f of t, which is e to the at, and then times e to the negative st. And then this whole thing is with respect to t, so dt. And this actually has some properties of exponents that we can use to simplify it. So if you're multiplying with the same base, you add the exponents, which in this case gives us at minus st as an exponent. And if we wanted to, we could actually factor a t out of that. But what I'm going to do at this point is turn this into an indefinite integral and find an antiderivative, so the work is a little cleaner. So I'm going to try to do this indefinite integral right here. So I factored t out of both parts of the exponent, and now it's actually a relatively simple one. There should be a quantity a minus s in there by the chain rule, so the antiderivative is going to be 1 over a minus s, and then e to the a minus s times t, and then a plus c because it's an indefinite integral, but we don't really need the c there because we're actually doing the definite integral. So let's go back here, and we substitute our antiderivative. So from 0 to infinity, it's going to be an improper integral because of that infinity, so we want to use the proper notation, so it's the limit as t approaches infinity of this thing, and then minus what happens when you plug in 0 for t is that we get this. All right, and then when you look at this, that first limit as t approaches infinity kind of has an issue if a is bigger than s. If a is bigger than s, then that exponential is just going to grow without bound as t approaches infinity, so we need to add a restriction and say that s must be greater than a if this is going to converge. If s is greater than a, then the exponential ends up in the denominator and you get 0 for that part. So this part, with our restriction, is just going to go to 0. The second part, since it's e to the quantity a minus s times 0, that's just e to the 0, which is 1. So I'm getting negative 1 over a minus s. What I'm going to do is distribute the negative into the denominator and get 1 over s minus a. And we're pretty much done with this, so let's summarize it as the transform of e to the at is 1 over s minus a, provided that s is greater than a. Alright, so that's it. Let's try to do the next one. So the next one is a little more complicated. We want the transform of te to the at. And we're just going to set it up by definition and kind of go through it. So it's integral 0 to infinity, it's f of t, e to the negative st, and then dt. This, again, you can kind of clean up with those exponents. So we have this, and I factored that time. Okay, I need to integrate this, so I'm going to do the indefinite integral, and t e to the something times t, I know from experience is going to require integration by parts. And this one's, it's a little messy, so I would actually rather use the tabular method because that's just, in general, more organized than I tend to be when I don't use it. And you can always use it when the derivatives of u eventually go to 0, which they will in this case because I'm going to let u equal t. So I have uv and then the sign. So in the first column, you start with your choice of u, which in my case is t, and then down the column you just keep putting the derivative. So the derivative of t is 1. If I did it again, the derivative of that is 0, and that's how I know this is actually going to work out for me. The v column is where you might make your mistake. You don't put dv there, you actually put v. So dv is e to the a minus s times t. So I need to integrate that. That's the integral that we did last time. So that's going to be 1 over a minus s, e to the a minus s times t. And then I need to integrate it again so it can match up with that 1. So you pick up another factor of a minus s, so we get that. And then the sign, we actually only need to remember that between the first two terms of integration by parts, there's a minus sign. All right, and when I write this down, the indefinite integral that we found is going to be equal to, so you multiply, within each row, you multiply u and v, and then you just put the sign in between terms. So it's going to be t over a minus s, e to the a minus st, then minus, and then 1 times that version of v there, and we get this, and then technically there's a plus c. This, if you look at it, you factor a bunch of things out, but the only thing that's really useful to factor out, I think, is the e to the a minus s times t. So I'm going to write it like this, and I'll use that as my antiderivative. So let's go back to the definite integral. So we have our antiderivative, and we're evaluating from 0 to infinity. The infinity makes it an improper integral, so we write the limit as t approaches infinity of this thing. So that's like subbing in the upper bound, but since it's infinity, it requires its own notation. And then minus, we're subbing in 0 for t. You always got to keep track of what you're subbing for, because there's there's t, there's a, there's s. We're subbing for t because the integral is with respect to t. The limit, the same problem exists that we had last time. If a is bigger than s, that exponential grows without bound, so we throw our restriction on there and we just say that s is bigger than a. If that's the case, then the first part, as t approaches infinity, that's just going to zero out, so we don't have to worry about it. And the second part, e to the exponent times 0 is just e to the 0, which is 1. And so we get minus negative 1 over that, so that's just positive. And we're basically done, except so it looks like the transform of just e to the at. We're going to reverse that because the quantity a minus s squared is the same as the quantity s minus a squared, and then they look the same, easier to remember. So here we go. So we're going to reverse it so it looks like 1 over the quantity s minus a squared, and then don't forget our restriction, and we're done. All right, so those are 2 transforms that you can definitely do by hand. They are definitely worth memorizing. They come up a lot. I hope you found this helpful, and good luck.